Hello guys, welcome on Tesla Adventures. In this video, today we are going to discuss the second law of thermodynamics and its various statements as well as Carnot engine and all the details of Carnot engine. Now first of all, let us see that in the second law of thermodynamics there were three scientists which contributed in stating the second law, and one of them was Clausius. And according to Clausius, second law of thermodynamics states that it is impossible to construct a device which operates on a cycle and whose sole effect is to transfer the heat from a cooler body to a hotter body. In the simple words, if I say the Clausius statement again, then it says that it is impossible to construct any cyclic engine or a device which is working on a cycle and which can transfer the heat from the cooler body to the hotter body without taking any aid of external source. So without taking any help of external source, no device can convert the complete can in fact can transfer the heat from the cooler body to the hotter body without use of any external help. Now, Kelvin-plank statement says that it is impossible to construct a heat engine that can convert all of the heat from the hotter reservoir to the useful work without losing any heat to the colder reservoir. Which means that Kelvin-plank stated combinedly, because initially they stated their individual statements, but finally they came to a common conclusion and they combinedly stated this statement that you cannot convert any heat engine, you cannot construct any heat engine which can convert all of the heat taken from the hotter reservoir into work done. Which means that if it is converting the complete heat into work done, then obviously its efficiency would be 100%, and according to them we cannot construct any heat engine of 100% efficiency. So this is a Kelvin-plank statement. Now there was another statement, entropy statement, that the entropy of an isolated system either increases or remains constant in any spontaneous process. It never decreases. We will have a detailed analysis of this statement in the video of entropy. So let us just skip this statement for now, and let us move on to the Carnot engine. So you can see that this is a Carnot engine, and Carnot was a scientist which proposed ideal heat engine which is working between two reservoirs, hotter reservoir and colder reservoir. And he assumed that this is the ideal heat engine, and obviously the efficiency of this heat engine is not 100%, obviously, because 100% efficiency is not possible. But Carnot engine is the ideal heat engine, which means that no other engine which is working between these two reservoirs can have an efficiency which is greater than the efficiency of a Carnot engine. So this is a proposal of an ideal heat engine. Now, heat engine is obviously a device that converts the heat into mechanical work, and we in our day-to-day life are using these useful engines in our cars, bikes, and all the devices which have some engine. So this is a engine, and you can see this is a block diagram of a heat engine, which says that this engine takes some heat from hotter reservoir, and it uses that heat to do some amount of work done, and the remaining amount of the heat is extracted to the colder reservoir. Now in our realistic engine, I would be discussing the petrol and diesel engine separately in a separate video, but let me tell you briefly that in a realistic engine, uh, the engine burns the fuel and gets the heat from the fuel burning, and therefore the source of engine is the fuel which is burning, getting burned, and engine is extracting the remaining amount of heat to the surroundings. So the sink in the case of engines is the surroundings near the engine, and therefore you must have seen that the efficiency of cars and bikes in the winters is good. I'm not talking about the starting problem. You might have noticed the starting problem of engine in winters, and that is due to the freezing of electrolytic solution inside the battery, and that is another problem. But after getting started, engine performs best in winters, because in winters the surrounding temperature is quite low, and therefore it is very easy for engine to extract the extra amount of heat to the surroundings, as compared to the extreme heats that is seen nowadays in summers. So in summers the surrounding temperature gets quite high, and due to that high temperature, engine is not able to extract the remaining amount of heat to the surroundings. That is why the efficiency of the heat engines in summers is not as good as that in winters. So now let us see that Carnot suggested that his heat engine, that is Carnot engine, works in the 4 cycles. So you can see this is a 4 cycle heat engine. In the first cycle, there is isothermal expansion of the gas, which means that this gas absorbs some amount of heat from the surroundings, or in fact from the source, that is hotter reservoir, and this gas expands isothermally from this point to this point. Then that this gas is being kept on an insulating pad, which insulates this complete piston from the surroundings, so that no heat exchange could occur between the gas and the surroundings. And then this gas is expanded adiabatically. So this is adiabatic expansion. Then this gas is being compressed isothermally, which means that it is allowed to extract the heat to the surroundings, and surroundings in this case is technically referred as the colder reservoir, and the colder reservoir is technically referred as sink, and the hotter reservoir is technically referred as source. Okay, so this is a colder reservoir, and it extracts the extra amount of heat to the colder reservoir, that is sink, and that is isothermal compression. Its temperature remains constant, and again we insulate the complete chamber from the surroundings, so that there is no exchange of heat from the surroundings. And then again we compress this gas to bring it into the initial state, which was the first state. So this is a complete cyclic process, and in this process in this cycle there are 4 processes. First process is isothermal expansion, second process is adiabatic expansion, third process is isothermal compression, and fourth process is adiabatic compression. And the gas returns to the initial state finally after getting through these 4 processes. Now let us do some technical analysis of the Carnot cycle, and let us see that if the initial pressure, initial volume and initial temperature is P1, V1 and T1, then in isothermal expansion obviously the new pressure would be P2, volume V2 and temperature would remain same. Then in adiabatic expansion all of these 3 variables would change. Then in isothermal compression again temperature would remain same, and then in adiabatic compression all of these 3 variables will change to the initial state. So first of all let us see that in the first case, in the first process, that is isothermal expansion. So in isothermal expansion we can write the process equation as P1 V1 is equal to P2 V2. This is the first equation. P1 V1 is equal to P2 V2. Now, and we can also see that in this expansion process, delta U will be 0 because it is an isothermal expansion, and the heat is absorbed by the gas. Heat absorbed by the gas will be equal to work done by the gas, and the work done will be equal to nRT ln V final by V initial, that is V2 by V1. This is equation number 2. Okay, now in second process, which is adiabatic expansion, we can write down the process equation, that is P2 V2 to the power gamma is equal to P3 V3 to the power gamma. Okay, and this is equation number 3. And the work done in this process is equal to the heat supplied to the gas, and in fact in this process we know that heat supplied is 0, and therefore delta U plus dW will be 0. So dW will be equal to minus of delta U, and we are just dealing with the heat absorbed. So let us see that heat absorbed in this process is 0, and the work done dW will be equal to nR delta T, and you can see that in the expansion process work done would be positive, so this would be positive. And if in this expansion we have to write nR delta T, and delta T is either T1 minus T2 or T2 minus T1. Let us take the mod and upon gamma minus 1. This is the work done in this process. So this is equation number 4. Now in the third process, that is isothermal compression. Isothermal compression. In this process, you can see that P3 V3 will be equal to P4 V4, and this is equation number 5th. And the heat exchanged by the gas in this process would be equal to the work done, because delta U is 0 and work done is negative, so heat is rejected by the gas to the sink in this process. So this is QR, that is heat rejected. So heat rejected will be equal to work done, and the rejected heat will be equal to nR T2 ln V final by V initial. Now when we are writing the rejected heat already, and we know that work done would be negative, therefore heat would be rejected. So now when we are writing the rejected heat, then we have to use a positive sign, and we have to bring a positive value of this term. So we know that V4 is less than V3, and if I would write ln V4 by V3, then it would be negative, because the function of log should not be less than 1 for positive values. So to bring the positive value, I am writing it down as V3 by V4. What I am trying to say is the fact that if I just write down the formula of work done as nR T2 ln V final by V initial, then it would be negative, because V final is less than V initial, and I have used that negative sign in flipping this value, and I am writing that it is the heat rejected already. So this is equation number 6. Okay, and in this, obviously work done is the same, and work done would be equal to, let us minus of Q rejected. Okay, and let us take the new page. And the fourth process is adiabatic compression. So in adiabatic compression, you can see that P4 V4 to the power gamma will be equal to P1 V1 to the power gamma. This is equation number 7th. And the work done in this process would be obviously negative. So let us write down the work done as nr minus of nr delta t, because this work done would be negative. So delta t would be, let us suppose that T1 is greater than T2. We are supposing that T1 is greater than T2. So we can write down the work done as minus of nr T1 minus T2 upon gamma minus 1. This is equation number 8. Now you can see that if we multiply this equation 1, equation 2, in fact equation 3, equation 5 and the equation 7, then we would be getting P1 V1 into this is P2 V2 to the power gamma, this is P2 V2 to the power gamma into this is P3 V3 into P4 V4 to the power gamma, and that is equal to P2 V2, the other side of the equation, and P3 V3 to the power gamma, P3 V3 to the power gamma, and this is P4 V4 and P1 V1 to the power gamma. So cancelling P1 P2 P3 P4 P1 P2 P3 P4, and it would be V2 V4 to the power gamma minus 1 is equal to V3 and V1 to the power gamma minus 1. So V2 V4 will be equal to V3 V1. So you can see that V3 by V4 will be equal to V2 by V1. This is a relationship of volumes in the cyclic process, and we know that the heat absorbed by the gas is obviously in the first stroke, that is isothermal expansion. In this stroke, gas was expanded isothermally, so it required some amount of heat, and we have already written that absorbed heat, and this heat is being absorbed from the source, the reservoir of higher temperature. And in the isothermal compression, in the third stroke, we can see that heat is being rejected to the sink, and we have already written the rejected heat. Now let us talk about the efficiency of the cycle. We already know that efficiency of the cycle is work done upon heat supplied to the gas. And work done, you can see that work done in this process W will be equal to Q absorbed from the reservoir, hotter reservoir, minus Q rejected to the sink. Okay, so work done will be equal to Q absorbed minus Q rejected upon heat supplied is obviously Q absorbed. So neta will be equal to 1 minus Q rejected upon Q absorbed. And we have already written the values here. So you can see that if we write down Q absorbed, then it would be nR T1 ln V2 by V1. Q absorbed is nR T1 ln V2 by V1, and Q released or Q rejected is nR T2 ln V3 by V4. So Q rejected is nR T2 ln V3 by V4, and Q rejected upon Q absorbed will be equal to T2 by T1. So neta, because we have already proved that V3 by V4 and V2 by V1 are equal in this case. So neta would be equal to 1 minus T2 by T1, or neta is equal to 1 minus T2 was the temperature of the sink to which heat was extracted, remaining heat, and T1 was the temperature of source from which heat was absorbed. And this is the efficiency of the Carnot engine. And obviously this efficiency formula proves that we cannot have if we say that efficiency is 100%, then T sink will be either 0, which is impossible, and T source will be either infinity, which is also impossible. So no engine can have an efficiency equal to 100%. And obviously, if let's suppose a boy constructed a heat engine whose sink temperature was 300 Kelvin and source temperature was 400 Kelvin, and he claims that his efficiency is 30%, his engine's efficiency is 30%, then we have to verify his claim, that whether he is doing a right claim or he is doing a false claim. So we know that the efficiency of a Carnot engine is 1 minus T sink by T source, and efficiency will be equal to 1 minus T sink is 300 and T source is 400, so it would be equal to 1 by 400. And if we convert, in fact, 100 by 400, and neta will be equal to 1 by 4, so in percentage it would be equal to 25%. So if a Carnot engine, which is an ideal engine, is working between these two temperatures, then its efficiency is 25% only, and this boy is claiming that his engine has an efficiency of 30% working between these two temperatures. So his claim is not correct, and he is doing a false claim, because we know that for a given set of temperatures of source and sink, it is impossible that some other engine has an efficiency that is greater than the Carnot engine, because Carnot engine is an ideal engine. So this was the complete Carnot engine and second law of thermodynamics. In the next video, I'll be bringing the combination of heat engines, in which we'll study that how to calculate the efficiency of a series combination of heat engines. And in the upcoming videos, we'll be bringing the refrigerator and reverse Carnot engine along with entropy. Thank you.